Hello, I'm Alex Berka and I'm affiliated to iSynchronize. Thanks for joining this presentation on alpha-RAMs. Problems in concurrency and parallelism provide motivations for introducing new models. Here's a selection of papers describing some significant ones. The first main reference is a review from Skillicorn and Talia from over 20 years ago, which is still relevant today in my view. They observed that the von Neumann network and associated processor networks, and I would include multicores here, were ad hoc because, unlike the von Neumann model for sequential computing, they preceded the development of a general-purpose model of parallel computation. Basically, the theory required for parallelism was immature and was developed after the technology. For your consideration, I'll be presenting a novel candidate for a theoretical model shortly. Back to von Neumann, there were well-known difficulties in shielding programmers from low-level tasks, in scaling programming models and architectures for larger networks, and porting code across different network sizes and topologies. Von Neumann issues had consequences for efficiency. In an IBM study in 2012, data centers were surveyed which acknowledged massive concurrency, but also highlighted the scandal of low processor utilization, which averaged at 17%. An earlier McKinsey report indicated values of 6 to 12% were typical. In a blog from 2016, Rowe observed how multi-core bottlenecks have driven up the usage for GPUs and FPGAs in data centers, which are rapidly taking up much of their workload. In the second main reference, which addresses concurrency, Abramsky criticizes the explosion of process algebras for specifying concurrent programs. There are too few constraints in defining them, and he highlights the lack of a grand theory of concurrency. He expresses the hope that theories from physics will come to the rescue, and I'll be returning to that idea shortly. In what seemed to be a bid to rescue non-deterministic concurrency, Peyton-Jones acknowledged the dominant technology at the time for concurrent programming, locks and condition variables, as being fundamentally flawed. Peyton-Jones argued software transactional memory can save the day, but the approach does incur overheads. Semantics in theories of non-determinism are prone to combinatorial explosions. In 2006, Lee argued non-determinism renders larger programs incomprehensible because it introduces state explosion. This makes the establishment of semantic equivalence between threads intractable, and he calls for deterministic forms of concurrency. Alpha-RAMs provide machine concepts underlying a project called synchronic computation, and shortly I will mention two aspects of the project to provide context. The benefits of alpha-RAMs, which I describe as the first simulable bit-level parallel machines, now follow. A machine called the synchronic ARAM is a candidate for a general-purpose theoretical model for parallelism. And if you remember nothing else, please remember this claim that the machine's set of just 4 primitive instructions is sufficient to express any finite parallel or concurrent process. Alpha-RAMs give languages a simple semantics, so it should also be easier to reason about them. Ultimately, any program has to run on a machine. I'm suggesting it's easier to intuit programs running on a device rather than as a complex expression evolving over time. As the machine is bit level, lightweight implementations of concurrency protocols and other constructs can be conceptualized without introducing complexity from the particulars of higher level models. A requirement of any scientific model is to make it possible to simulate not just simple examples, but also more complex what-if scenarios. Alpha-RAM simulations of compiled programs tractably detect errors and misconceptions, which is better for language design. Now, formal models are usually abstracted from various physical considerations. Although alpha-RAMs are fine-grained and do not immediately provide clues for architecture, they do provide an opportunity for innovative hardware by allowing the introduction of a succession of physical constraints in a least restrictive order, thus reducing bias from existing architectures, leading to innovative design. Finally, a new model affords novel and unknown avenues for developing software, hardware, and theoretical frameworks. Now, Two aspects of synchronic computation to provide context for alpha-RAMs. Firstly, functional programming and some semantic treatments of process algebra propose that languages can and should be abstracted from hardware. Referring back to Abramski's aspiration that physics might come to the rescue of concurrency, it is suggested here that what is needed is not so much physics as a physical-like machine environment, or at least an abstraction of one. Synchronic computation argues that complete abstraction from hardware is overkill because important opportunities for implicitly avoiding data hazards and deadlocks are lost. It is claimed that an abstract machine environment can maintain abstraction whilst avoiding side effects. Secondly, in agreement with Lee in the reference from the previous slide, the current approach argues that deterministic parallelism should try to subsume non-deterministic concurrency for most, if not all, purposes, barring perhaps something like an off-planet internet. Non-deterministic concurrency workbenches are usually developed and run on deterministic processors after all. Finite alpha-RAMs are now finally described. A brief mention about notation. Capital N italicized is the set of integers, and N subscript M is the set of integers from 0 through to M minus 1. And capital P italicized is the power set symbol. The ARAM is a generic term for a memory configuration, which is formally defined here in the style of denotational semantics. An ARAM has a finite memory block of registers composed of bits like a finite register machine. P is an integer greater than or equal to 3 and is called the offset, which defines the number of bits needed to encode the bit index of a register, which contains n equals 2 to the p bits. Q is the number of bits in a register allocated for an opcode, of which more later. The number of bits remaining in a register to encode a register index in the memory block is n minus p minus q, which fixes the maximum number of addressable registers in the block to 2 to the n minus p minus q registers. Sigma is a memory function which takes register and bit indices and returns the contents of the bit location. Big sigma is the set of all memory functions. Mu is called the initial marking and is a subset of instructions, one per register, which are activated in the first machine cycle. A marking generally represents the subset of registers whose instructions are to be executed in the next cycle. Markings may not contain register 0, which is reserved for machine status bits. Big M is the power set of all markings. Now, a machine state is the pair of the memory function and the marking. Eta is some state transformation function on memory and markings, and in this treatment is total. Eta could be a partial or a relation in order to express non-determinism. A run commences with an application of the function and repeated either indefinitely or until a halting condition arises. This framework is quite flexible and allows a range of machines by changing the definition's tuples. The slide also presents an example called the synchronic ARAM. From now on, I will just call it the ARAM, which is less of a mouthful. In this instance, P equals 5 and a register has 32 bits. The memory block has about 33 million registers and occupies 134 megabytes and is big enough to support some massive parallelism. Please see the formal definition, which is appended to the slides, which does not contain the errata of the main report mentioned later. The alpha-RAM is an ultra-fine-grained, globally clocked, simultaneous read and exclusive write machine where the transmission of information between any two registers or bits occurs within one machine cycle. Propagation delay of 0 is sometimes called zero-time semantics, which all formal models have in some way. Propagation delay could be introduced as a shifting string of markings based on some distance metric applied between registers, and other physical metrics for routing, placement, and chip area could also be introduced to be able to reason about such things. In the von Neumann model, program control passes from one register containing an instruction to another, so that only one instruction is ever active per cycle. In the ARAM model, multiple registers or instructions may be active per cycle and execute in situ. The machine has a process in memory character. Any module represented in memory can potentially be active in a cycle, which is helpful in conceptualizing a maximum parallelization of code. The ARAM's instruction format is displayed in Table 1, and the instruction set is in Table 2A. XY in brackets designates the yth bit of the xth register, where x is the register index and y is the bit index. Subject to some restrictions, any register is capable of either holding data or of executing one of 4 primitive instructions in a cycle. The instruction with opcode 00 writes 0 into xy. The instruction with opcode 01 writes 1 into xy. Opcode 10 is a selection instruction called cond, which inspects the bit stored in xy and marks the next or next but one register for activation in the following cycle depending on the bit value. Opcode 11 is a jump which implements a parallel fork amongst other things. It can mark the instruction in register X in the following cycle and also those in subsequent registers up to X plus Y. The machine assumes no ALU with the standard arithmetic functions. All operations have to be defined using only the 4 primitive instructions. In practice, there is a frequent need for self-modifying code. In Table 2B, the 4 instructions are hopefully shown to be enough to express any finite form of parallelism and concurrency, providing the block is big enough. The granularity of the instructions is such that it is hard to see how the machine can impose any bias on a conceptualization of a process. The instruction set is also simple enough, in my view, to teach secondary school students how to parallel program. Instructions and processes are concurrent if they appear in the same markings, and each instruction requires exactly one resource, a register, so the model is very simple and explicit. This contrasts with the elaborate structures I've seen that have been devised to give process calculi a true concurrency and resource semantics. The orange registers here illustrate how the marking may evolve in time. The first cycle must set the busy bit of the machine located in 00, and if the machine halts legally, the last cycle must contain only one instruction which resets it. So this is just an illustration of a run. So we have a few cycles with multiple registers, and then the final instruction must reset the busy bit. The state transformation function's formal definition is based on the instruction set and an error detection scheme and is appended. A machine run consists of the function being repeatedly applied to the machine state either indefinitely or until a special termination condition arises. An ARM process has an explicit denotational meaning and is a sequence of pairs of memory blocks and markings. In contrast to multithreading, where a process is viewed as a collection of sequences of instructions, an ARM process is a sequence of collections of instructions. The model's definition incorporates error conditions that halt a machine run if ill-defined or nonsensical behavior is detected, including multi-set markings and multiple writes to the same bit. The error scheme is described in more detail in an appended slide. The removal of parallel-related contentions at the most primitive level of machine activity contributes to eliminating contention in higher-level programming. Now here's a program example that runs a pair of 2 input AND gates in parallel to implement a 4 input AND gate. Not having presented higher-level languages yet, a trivial example must suffice here. Register 24 stores the input in bits 0 to 3, a temporary bit in bit 4 to store the result of the second AND gate, and the final result in bit 5. The code for the first gate includes a carry thread which transfers control to the next stage of the program. So here we begin the run, and the first cycle sets the busy bit, jumps to the rest of the program, starts the 2 AND gate threads. We're starting to test the 2 sets of bits, and they're all 1. And now the second AND gate is writing its result, and the exit thread is testing that result and jumping to writing the final result in bit 5 there. And then finally we we reset the busy bit, and that's a run of the program.